we have Johannes Zierenberg from the Max Planck Institute for Dynamics and Self-Organization from Göttingen with us. Johannes, please.
Thank you very much. So thank you for the introduction, and I would also like to thank for the opportunity to present our work in this format, which is very new and exciting for me. This is such an online workshop. So in fact, I'm sitting right now in Spain, and so otherwise this would have been costing a lot of carbon emissions. So I really like this idea of putting this online together. And before I start, let me introduce you briefly to the team that did most of the work. So can you see my mouse?
Yes.
Yes.
Oh, perfect. So this is Jonas Zierenberg. So then you can have some idea about the faces. This is me. This is my face. This is Paul Spitzner. Here we have Michael Bibral, Joao Pinheiro Neto, Michael Wilczek, and Viola Priesmann. So we are the core team of what happened in the past weeks, where we tried to infer the spreading rates of the COVID-19 outbreak in Germany. So we focused on Germany, on the whole German to start with. And what we actually wanted to do is we wanted to describe the spread of the outbreak in Germany by a simple mathematical model. And I'll tell you in a second why. And then we wanted to infer the parameters of this mathematical model. And in particular, you wanted to know the uncertainty of these parameters. And then we wanted to use them to forecast future scenarios where we could look at different things that could have happened, and particularly also to propagate the parameter uncertainty. And the parameter the mathematical model we chose is similar to the previous talk, the SIR model. Let me briefly introduce the dynamics. So let's say in Germany we have a couple of people. These are the black people here, and there's an infected person, and that can spread the disease. And at some point, this person can get recovered, but the disease is continuing to spread. So we just put all these people into different compartments, and we call them the compartment of susceptible people, the compartment of infected, and the compartment of recovered people. And then every person can go from one compartment to the other. So for example, an infected person can spread the disease with a rate lambda to some susceptible person, and this becomes infected. And any infected person can recover at a certain rate nu. And we can express this SIR in these discrete differential equations. It's very similar to what we saw before, just a little bit different notation. So we have the per individual connection spreading rate, so to say, introduced here. So we get an extra term 1/n here. So we see that the number of susceptible people changes over time according to this fraction that depends on the current number of infected and susceptible people, and vice versa. The pool of infected people increases by this amount, but decreases governed by the recovery rate. And for a large pool of susceptible people, the dynamics is essentially controlled by the growth rate, because this factor here is just 1. So the growth rate, the effective growth rate, is just the difference between this spreading rate and the recovery rate. And this is then essentially multiplied to the path state. So why did we want to have a simple model? Because we wanted to do Bayesian inference. And the main idea here is that we wanted to estimate the probability of seeing model parameters given the observed data that we have, but also including our prior knowledge about what we know about the disease. So the main idea is that we want to sample the posterior distribution using Markov chain Monte Carlo simulations, and where we wanted to see the probability of having certain parameters describing the data, which is proportional to some likelihood that we formulated, where we see the probability that we observe the data for some parameters. This is essentially driven by our dynamical model, and then combined with the prior of previous parameters of the parameters. And let me just illustrate this, how this works, on 2 examples. So for example, the recovery rate, we have a rough idea that that people can be infected for about 8 days. That was kind of going around in media and in the literature. So the recovery rate is fairly constrained to be 0.12 in terms of days. So we formulated a narrow prior. This is a log normal distribution. This is the gray line here for this recovery rate. And then we did our sampling, and we see that the posterior that comes out is fairly consistent with this prior. So the data didn't constrain this. And on the other hand, for example, we also fitted the scale, the width of this likelihood function. I won't go into detail, but since we had no idea about that, we chose a very flat prior and essentially let the data constrain this parameter. And the last thing that we introduced is because we were also interested in a dynamical model is we introduced change points, but we didn't do that continuously, but we really said, okay, let's say that governmental interventions really act as change points in the spreading rate. So we have some spreading rate lambda that's constant over time up to some intervention point, and then we have some sort of a linear crossover to some other plateau of a new spreading rate. And this is just a case where we have three different scenarios. Nothing changes, there's a slight change, or there's a strong change in the spreading rate. And the interventions that we considered are the three main interventions that happened in Germany. The one is on was on March 9th. We had the cancellation of large events with more than 1,000 participants, or around March 9th. Then we had March 16th, where the schools were closed, child care centers as well, and majority of stores. And then there was March 23rd, where we had the contact ban introduced and closing of all non-essential stores. And without going into too much detail on how this whole machinery works, I can just show you what we got from this. So what we wanted to do is to quantify the governmental interventions. And this is a huge figure, but I'm going to go through this slowly. So let's focus on this part first. So what we had is data. These are the blue dots here. This is the new daily cases confirmed in Germany. And this is typically what we see in the media. It's the total confirmed cases in Germany, which is growing, but this kind of is variable over time, right? And what we did now is that we let our model generate different trajectories and looked at the likelihood and particularly also combined with prior to see which parameters describe this well. And then we get distributions for these parameters. One particular thing that I want to focus on is that in order to do this properly, we had to introduce a reporting delay between the real effect of the disease in the community, and the time when it's actually recorded. So this is the reporting delay, which is has three contributions. It's on the one hand side, the biological incubation period. Then we have a delay from first symptoms to symptoms motivating a test, and a delay before testing results come in. So this gets inferred by our model to be roughly 9.5 days. And this is not completely similar to what we put in as a prior. So this is constrained by the data. And it's consistent with what one would expect from the literature to actually observe in Germany. And then what we actually got out is this time-dependent spreading rate, and with these three interventions, and in particular, because this is the model where we put all three interventions in, we can see that March 9th, so the cancellations of large events, they were roughly also fitted by our model around March 8th. And they just reduced the spreading rate to something like 0.25, which is still above the recovery rate. So we would still expect an increase in new cases, which kind of would have gone up here. Then we had the second intervention point. This is here on March 16th, where we had the closing of schools, and we see that this lowered the spreading rate to 0.16, which is still above the recovery rate. So we are right here now, this plateau. And this would have been this case here, where we would still observe an increase of cases. And only the last intervention, where we had introduced the contact ban and the closing of all non-essential stores, that really reduced the spreading rate, presumably below the recovery rate, so that we can actually now see clear decay in new cases over time. And then we can use this model and forecast what happens in the future, in this case, under the assumption that nothing changes. And also we compared to different realizations of models like 1, 0, 2 or 3 change points. And we found that this currently is the model that best describes the data. And then we can do forecast scenarios. So for example, we can think about what happens during Easter. And we know a lot of people did visit their families, even though they might have not, or maybe not supposed to. So we would maybe expect that there's a slight increase in the growth rate again, but it's probably just a bump. And then we can think about what happens now when we relax our interventions or restrictions. And there's actually 2 scenarios. One is stays the same or it increases slightly. And we can see this also now or we can use our model where we now, disclaimer, so we now have a new model here, which also incorporates the fluctuations over weeks in reporting, because this is actually also an important effect. And we can see that if everything stays fairly well behaved, we still are on the track of decaying new cases. But if now things just go above 0 in terms of this effective growth, we kind of just get back into the exponential growing phase. So this kind of can be used in order to be aware of how to deal with future potential interventions if we really want to get down to a level where we really want to track individual cases, for which we would say that we would kind of get below 1,000 new cases per day, or even fairly well below that. So as a summary, we started with inference of model parameters on the level of Germany in order to propagate the parameter uncertainty into future scenarios. We need to have a very simple model for this, because otherwise this whole Monte Carlo sampling would just explode in computational complexity. And the next steps that we are doing is now hierarchical inference on the level of federal states, together with a team from Alexander Ecker, in order to really boil this down to the different federal states, in order to get a bit more heterogeneity in the model, because right now we have this well-mixed assumption of SIR models on the global state of Germany. So we're curious to see what effects come in from there. And with that, I come to acknowledge this very nice work together the past 4 weeks with this team, the funding, which I forgot to mention in the beginning. And I would like to thank you for your attention.